One of the properties that we're going to talk about now is the property that we need when we talk about amount of atoms and molecules. It's a very important property and it's called the mole. And that mole is related to mass and it's related to counting number of atoms and particles, but students may have some trouble to really understand it, at least some students. So let me just give you a parallelism, an example of the way that we use mole. Hopefully everyone is familiar with the term dozen. When we talk about dozen, we say that 1 dozen is equivalent to 12 entities. So 1 dozen of eggs, it means that it's 12 eggs. So how many dozens are in 24 eggs? So 24 eggs, knowing that 12 eggs is 1 dozen, you have 24 over 12, you have 2 dozens. Okay, the same for 50 would be 50 over 12, so you could calculate the number of dozens. The same application, the same strategy we will use when we talk about moles. 1 mole is a way to wrap a lot of atoms or molecules. How much? How many? So 1 mole, if you will, is the dozen of the atomic world and is this big number. So the same way that 1 dozen contains 12 entities, 1 mole contains how many? These many. 23 entities. Okay, it could be atoms, it could be molecules, it could be eggs, if you will. Okay, not very practical to talk about 1 mole of eggs. It would be a lot of eggs, but it's definitely practical for talking about molecules and atoms. Okay, by definition, this number is the number of atoms that exist in 12 grams of carbon-12, the isotope 12 of carbon. Okay, and this number is called the Avogadro's number, named after Amedeo Avogadro, the Italian scientist. And so again, I want to emphasize that a mole is not a unit of mass. It's just a way to count entities, a way to count molecules, atoms, or chairs. But in our case, this huge number will be convenient because, as we said many times now, the atomic world is very small, so there's a lot of atoms in, say, 1 drop of water. Okay, so we will have to use this atom quite often. Okay, so let me talk about how we can connect moles and mass. Let's say, for example, that we have 12 red marbles, and the red marbles are somewhat heavier, 7 grams each, and you have 12 yellow marbles, and they are 4 grams each. Okay, so if you put 12 yellow and 12 red, of course, because the red are heavier, they're gonna sink more on the scale. The same can be said about elements. So in this case, we are measuring, notice that this is 1 mole of iron, and 1 mole of sulfur. So if we were to put in a scale 1 mole of iron and 1 mole of sulfur, because the iron atoms are heavier, of course, so you'll end up having more mass. So that's pretty much the relationship, and this relationship between mass and mole for elements, it's called atomic weight. The atomic weight or atomic mass. Let's call it atomic mass to be more precise. Does that make sense? So we will talk about the atomic mass in the next slide in the periodic table, but notice that the atomic mass, and these numbers are approximate, but the atomic mass of elements is related to more or less to the number of protons and neutrons that the nucleus of that specific element have. Okay, just to have so that you have a rough idea. So what can we do with it? Notice, for example, that it says carbon has this atomic mass. Okay, and the atomic mass will help you move from mass, number of moles, and number of particles. So let's say, for example, so what is the conversion between mass and number of moles? That is what we have been calling atomic mass. For example, if you have 10 grams of carbon, how many moles do you have? We will use the atomic mass. It says that the atomic mass is 12,011, so 12,011 grams in 1 mole. Again, the atomic mass relates grams and moles. So how many moles do we have? It's 10 over 12,011, whatever the calculator will tell us. How can we convert moles and number of particles? For that, we will use Avogadro's number. So using the same example, how many particles, how many atoms of carbon there are in 10 grams of carbon? So if you have 10 grams of carbon, we need to first convert it into moles. So that's important. You cannot go from number of particles to mass without going through the number of moles. So first we use, as we did here, the atomic mass, 1 mole. And now we will have to use the Avogadro's number that says in 1 mole of, in this case, atoms of carbon, there are 6.022 times 10 to the 23 moles. Sorry, not moles, atoms. Okay, and that's pretty much the general idea between converting mass, number of moles, and number of particles. That it's very important that you practice this relationship and how to convert mass, moles, and particles. Let's play some more with some more examples. In this case, so here you have, we already solved this. How many grams there are in 10 atoms of carbon? That's not correct. We solved, let me just backtrack here. We had 10 grams of carbon. So now it's a different kind of problem. So we have 10 atoms of carbon and we want to know how many grams. So again, let me just backtrack here. We are given number of atoms. We need to jump from here to here to get the mass. Okay, it's asking the mass. So let's do that. First we need the Avogadro's number that says in 6.022 times 10 to the 23 atoms we have 1 mole of carbon. That's the definition of Avogadro's number. And we go to the periodic table and we see that in 1 mole of carbon the mass is 1 grams of carbon. So again we will do 10 times 12,011 divided by 6.022 times 10 to the 23. I don't have a calculator here, but you plug this into a calculator and this will be the mass of carbon that exists. A different kind of example, for example, how many moles of molecules there are in 0.5 grams of oxygen. Careful with these kind of questions because it can be a little bit of a trap because it's talking about molecules. So oxygen doesn't refer to the atom of oxygen, it refers to the molecule of oxygen, which is what you breathe in, and it's the most stable form that oxygen alone as element is present in the atmosphere. So let's solve this. We have 0.5 grams of oxygen molecule and we want to know how many moles. Careful now because we can, if we go to the periodic table, it will say that the atomic mass of oxygen is 15.9 grams per mole. But notice that we have 2 here. So this will be actually the molecular mass. The molecular mass of oxygen will be 2 times 15.99, which is approximately 32 grams per mole. Does that make sense? So let's figure that out. Let's plug this into the factor conversion. In 32 grams, we have 1 mole of oxygen. Okay, so we're pretty much done here. 0.5 over 32, this will be moles of molecules of oxygen. This takes some practice, but in class we'll give you plenty of exercises to practice with, and there will be some quizzes, so we'll definitely be using these tools all throughout the semester, so I hope that you can get the idea.